In this Godot tutorial, I'll teach you how you can interpolate between various world states so that you can make the movement of various entities on the map look super smooth without increasing the bandwidth requirements of the network. Let's get started. In the last tutorial, we made sure that we can see other players on the map move around. We did so at 20 frames per second, as that is the tick time of our server. That made that the movement looks a little bit choppy, a little bit laggy, and that's of course undesirable. Now we don't want to increase the number of ticks of the server, because that will basically reduce the performance and reduce the amount of concurrently connected players that the server will be able to handle. So we are going to be interpolating. Now, what's interpolating? To explain to you how interpolation works, I'm going to be using a visual. We got the server that is sending out the world state 20 times per second, or every 50 milliseconds. And let's say, as an example, that our client needs to render the frame at 10 seconds, 285 milliseconds. There's a problem here because the client only knows where the players were in the game at 10:25. The packet, which contains the world state at 10:30, still has to be received by the client. It doesn't know that yet. And that packet may not even arrive. It's a packet after all, can get lost on the internet. So this is what's creating that choppiness, that lagginess, because we're updating that position only 20 times per second, as we don't really know where the player is going. So interpolation, how is it going to help us? With interpolation, we're going to say that we're going to render not at 10:285, but we'll tell the client to render the world 100 milliseconds in the past. Now you might be going, whoa, that means it's not real time anymore. And yeah, you're absolutely right, but surprise, surprise, this is industry standard. Name any MMORPG, name battle royales like Fortnite or PUBG. They all use this mechanic to buffer world states into an interpolation function. So what is this actually going to help us? Well, now we got two time stamps, 10:15 and 10:20, which have a world state with a position, a vector too. Now we can say at 10:185, well, we know where the player was, and we know where the player is going to go. And we know how much time the player is going to take to get from point A to point B. So we can pretty much calculate with this data on literally every single millisecond between those two world states where the player most likely has been. And if we make a small deviation in those calculations, this will automatically get corrected as we receive the next world state. So with this method, we are able to very accurately at any given time that a frame needs to be rendered, calculate where that player needs to go, where we need to place it, without actually having the server tick more ticks or tick faster, and without having to send any extra data over the network. Thereby, we are reducing the bandwidth requirements for our players, and everybody loves that. So now all we got to do is put this in the code, put it in our game. Good news for you, in this tutorial we'll only be working in one of our 4 projects for a change. So let's get started. The code I got selected right now is the code from the previous tutorial, number 11. And we have to unravel this code a little bit, put it into 2 different functions, the update world state right here and the physics process. I've renamed this old function to update world state old, and we'll be retiring all this code, but we will be making sure that we check, and I'll show you where the code has been replaced or updated or upgraded. So the first thing we can retire is these 2 lines on the top, because those 2 lines have been copied 101 into the update world state right here. The thing we do differently now is that we are going to append the world state we received from the server into the world state buffer. The world state buffer is nothing more than an empty array defined on the top. Now, before we go into these other lines of code, let me first show you what we're actually going to do with that buffer to make sure we can run all the calculations in a convenient way, let's say. So first thing we need to do is we have to determine the render time. That's the time of the frame that we're going to render. That's going to be a timestamp, and that's one of the 3 crucial timestamps to make this interpolation work. We do this by getting the operating system's time in milliseconds minus the interpolation offset. The interpolation offset is a constant on the top, which I have defined as 100 milliseconds. I would say start out development with 100, and based on the geography that your player base is in, you might want to reduce or increase it. Now, next thing is we have to make sure that the world state buffer has the correct build-up. What I mean by that, I've written, well, it's not code actually, it's just more an indication visualization. We want the buffer to not, keep on appending and collecting more world states as a player has a single gameplay session. Because if we collect world states 20 a second for 3 hours long, then that array is going to be super slow, super big, just going to eat up memory basically. So we want to make sure that we clean that buffer up constantly, and ideally the buildup of that buffer is going to be the same every single time, so we can make easy references in the calculations. So what we want is we want index number 0, the first index, to be the most recent past world state. So it's going to be in the past, but the most recent one in the past. And then the index number 1, or the second index, is going to be the nearest future world state. And then after that, we can keep on collecting any other world states. That might be more, that might be less, that doesn't really matter. So to get that, what we first do is we check if the world state has at least the buffer has at least 2 world states. If it doesn't have 2 world states, none of this code is going to work. We're going to throw errors. We don't want errors. That's not good for our game. So we check if we have at least 2 world states, else calculations won't work. Then, while the world state buffer size is more than 2, so it's going to be 3, 4, or 5, we're going to check if the render time timestamp is bigger than the timestamp of index number 1 in the world state buffer. Now, what does that mean? We're checking if the render time has become bigger than the nearest future world state, because if that's the case, it's not in the future anymore, and we can move the nearest future world state into the most recent world state, and we can move any other future world state that has a timestamp that's even further in the future to the nearest future world state. The way we do that is we simply remove index number 0, so that would not be the most recent past, but the timestamp before that, or the world state before that. We don't use it anymore. It's useless to us at this point. We simply remove it, and as we remove index number 0, everything is going to shift 1 position up, and we're again ending up with the right circumstances. Now, what's important is that you use a while function here, because it might be the case under some circumstances that you're going to have several of these packets that need to be deleted in order to get the right world state. That especially happens at startup of the game, and if you don't use a while loop here, most likely you're going to go out of sync, and then things are going to look really weird. So make sure you use while, not if. Then what we need to do is we need to determine, based on the timestamp of recent past and recent future and render time, 3 timestamps, how much time has passed expressed in a percentage from state in the past to state in the future. Because if we're very close to the future state, we want the position to be closer to the future state. However, if the most recent past world state is just in the past, 2 milliseconds in the past, we means that we need to render the position of the player very close to that state. To do that, we're going to be lerping that position, but in order to lerp, we need to have the factor between 2 positions that it needs to lerp in between. Now, if you want to look that up, you better be looking up lerp as in function. You can go search help, you can go lerp, and you can look up more information on how that function exactly works. So we're going to need that interpolation factor. We get that by taking the time that has lapsed from the previous world state, the one in the past, to the current render time, and we divide that by the difference in time between both world states that we are lerping in between. As we have that, we can now start looping over every single player in our world state and start determining its position based on the render time instead of based on the world state time. To do that, and that's basically where we're going to cross over into our old code, so that's basically this function or this line of code right here, we still have 2 deletions out of our world state here in the previous code. Previously, we were erasing the timestamp of the world state. Well, we have already used the timestamp of the world state here to determine the interpolation factor, but we haven't used it yet for any extrapolation. And timestamp that might be very handy in the future, so I don't want to be deleting it anymore. So we're not going to delete that. And also the deletion of the player ID, well, I've opted for a different solution which I think is a little bit cleaner. That is right here. First we check if that player is equal to the T of timestamp, in which case we continue. We don't delete it, we simply skip over it. We continue to the next player in the for loop. We do the same if the player is its own network ID. We continue to the next player in the for loop. And another check we have to do, if we have to make sure that the player that we're going over is available in both world states. If the player just logged in, it might be the case that that player is not available in the old world state. And if the player just disconnected, the player might not be available in the future world state. So we have to make sure that that player is available in both world states, otherwise the code would run into an error. Now, once we have all that, you can see we start going into very similar code right here. Now, instead of simply saying move player and then with the position of the world state, we are first determining the new position by lerping. This is where that lerp comes in. So we're going to take the position out of the world state in the past at index 0, the position out of the world state in the future at index number 1 in the buffer. And we're pushing that interpolation factor, which is going to be the same because we're basically got two world states. So that factor is always the same. That's why we define the factor one time on the top, and then we use it for every single player we're lerping over. Now, as we have the new position, now we take exactly the same function as before, but instead of pushing the position from the world state, we're pushing the new position that we have determined by lerping between two world states, one in the past, one in the future. Then here the code is pretty much exactly the same. Only difference is that instead of taking the player position out of world state player P, we now have to take it out of the world state that is stored in the buffer, and that's why it looks a little bit different. So with that, we are pretty much interpolating the positions, and our movement should look much smoother. And let me quickly delete this line of code, and I think we can give it a test. So I got my two clients. I've got two different usernames and password already set in. So I'm gonna log in on this side, gonna log in on this side, and now we can move around here. And as you can see, the player movement is super smooth. We don't have any of that choppiness anymore that we had in the previous tutorial. And of course, this one works exactly the same. That was it for today, guys. Hope you like it. If you did, smash that like button, hit subscribe. Don't forget that little bell icon to make sure that you don't miss out on our next episode. In the next episode, we're going to be taking a look at extrapolation. Extrapolation is pretty much the same process, but then what if we don't have a future state? What if the packets simply weren't reliable enough and we don't have a future packet? How can we still make sure that that movement stays smooth? Also, in the next episode, I'll address an issue that this code has created. Because now we are rendering 100 milliseconds in the past, the moment a player disconnects, the interpolation function basically spawns that player straight in again. So currently you can't disconnect without actually having the player disappear from the playfield. That's an issue that I'll address together with extrapolation in the next tutorial. Hope to see you then. Until then, keep on gaming, keep on coding. See you later, guys.